Okay, now we're going to look at another friction problem that introduces another issue into the situation, and that's tipping. So the first two problems that we looked at involved slipping, and now this one involves both slipping and tipping. And what we have is a 500-pound crate. That'd be this rectangular box looking thing. And so I'm going to go ahead and put a force vector here and say 500 pounds. And I'm going to put that vertically through what we're saying is the center of gravity, which is directly in the middle of this thing, and it's 3.5 foot up from the base and 2.5 feet up from the top, but it's directly in the middle of the box. So you got 500 pounds that are coming down like this. The static coefficient of friction for this situation, we're told, is 0.40. And what we're going to try to do is determine the maximum force P, and P is applied at a height of 4.5 feet above the horizontal surface. And we want to find the maximum value of that force that can be applied to the crate without causing the crate to move. Now, there's two ways it can move. One way is it can translate on the surface, and then the other way is it can tip over. So either we get a translation, which would be like this, or we get a tipping, which would be like this. So this one would be tipping, and this one here would be a translation or a slipping. Now, it's interesting to note that in this tipping model, the only thing that remains in contact with the flat surface is this corner of the block right here. So it pivots about that point as it tips. The only way that can happen is if the friction force that develops is large enough that motion, or the slipping motion, is prevented. So then the coefficient of friction acts right here at this corner and holds effectively this thing in place, and then it just tips over about that point. So either it slips or it tips. Now, in general, when a load is applied to a body like this, it either does nothing, or it slips, or it tips. In this case, though, they're wanting to determine an impending slippage and an impending tipping. Now, the question is really clear. Which one of those happens first? Because it could slip, it could tip, but how do we know which one happens first? And the answer is we don't. And the reason we don't is because we haven't addressed the question yet. So what we're going to first do is we're going to assume that it's going to slip, and we're going to examine that case. And then we're going to assume that it tips, and we're going to examine that case. Now, I'm going to get a P associated with slipping, and I'm going to get a P associated with tipping. One of those is going to be smaller than the other. The one that is smaller is the one that controls. Now, incredibly rarely you would get a situation where the slipping force is exactly equal to the tipping force. But in the real world, that's not ever going to happen. But I guess conceptually that could happen, in which case both these values would be the same. And so you would just say the load which causes motion would be a certain value, and you really wouldn't be able to tell whether it slips or it tips. But like I'm saying, that's just a very rare situation, and so I don't really think there's a reason to deal with it. So we're going to first look at impending slippage, and then we're going to look at impending tipping and see where we are.